Artificial intelligence is, at its core, a multi-layered computational system. It executes cognitive tasks by identifying complex statistical structures hidden within massive datasets. To understand how these systems operate, we have to separate realized technology from theoretical concepts. The capability taxonomy divides AI into three tiers: artificial narrow intelligence, artificial general intelligence, and artificial superintelligence. Modern enterprise AI operates entirely within that first tier. These narrow AI models are highly task-specific. They do not reason across domains, and they require massive volumes of highly specific training data to function. In a production environment, writing the raw mathematical algorithm represents only 10% of the actual job. Transforming a theoretical algorithm into scalable enterprise infrastructure means building an end-to-end stack. You have to select a learning paradigm, design a specific network topology, orchestrate a continuous machine learning pipeline, and execute hardware-level inference optimization. The foundation of this stack is the learning paradigm. This is the framework that dictates exactly how a model updates its internal logic to map data to outcomes. This matrix maps out supervised learning. In this paradigm, a model trains on annotated datasets, where every input is paired with a hand-labeled ground truth output. The model processes the inputs, makes predictions, and calculates its error against those fixed targets. That error calculation relies on specific loss functions, like mean-squared error for regression tasks or cross-entropy for classification. While highly accurate, supervised learning is bottlenecked by its absolute dependence on human-labeled data. Unsupervised learning bypasses this constraint entirely by autonomously discovering hidden statistical groupings within raw, unlabeled information. Then there is reinforcement learning. This is an action-based paradigm that forces an autonomous agent to learn through trial and error, constantly balancing the exploration of new actions against the exploitation of known high-reward behaviors. In a dynamic environment, like a hospital corridor, the input data isn't a static label. The system treats data as interdependent state-action-reward tuples, continuously adapting its route to optimize its goal. The choice of learning paradigm establishes the mathematics of the system, but those mathematical operations must be housed within a highly structured architecture. Deep neural networks provide that architecture. They simulate cognitive processes by passing data through multiple hidden layers. Each layer is built from individual nodes. Every node relies on specific weights, biases, and activation functions to determine exactly how it reacts to incoming data. This graphic displays a feed-forward neural network. It is an acyclic structure where data flows strictly forward, from the input layer directly to the output layer, with no continuous loops. For computer vision, convolutional neural networks use visual filters sliding over spatial data to extract features. Using shared weights, nodes perform the same detection job across inputs. Extracted data feeds into a pooling layer, retaining critical spatial information. This architecture excels at analyzing variations in handwriting, allowing logistics networks to process millions of handwritten zip codes with extreme precision. For sequential data, the architecture requires a recurrent neural network. Feedback loops allow node activations to propagate backward into previous layers, preserving temporal states. Augmenting loops with context layers, like long short-term memory networks, models long-range dependencies. Network topology is never an arbitrary design choice. It is a strict constraint dictated entirely by the modality of the data being processed. A perfectly designed neural network living inside a local development environment delivers no business value. To function at scale, it must be integrated into an enterprise pipeline. This workflow visualizes the machine learning lifecycle. It operates as a continuous feedback loop moving through data collection, pre-processing, feature engineering, training, validation, deployment, and monitoring. Within this loop, pre-processing and feature engineering form the heaviest operational bottleneck. Raw data is chaotic, incomplete, and highly unstructured. Cleaning and transforming that data into clear mathematical signals consumes up to 60% of a data scientist's workflow. If an operations pipeline feeds stale or unrepresentative data into a model, the algorithm will confidently execute biased, broken decisions at an enterprise scale. Once validated, the model moves through containerized deployment and CI/CD pipelines, where it is subjected to continuous tracking to detect data drift and performance degradation. Machine learning operations optimize a system for reliability. They ensure the underlying mathematical model survives the unpredictability of a live production environment. Even with a flawless pipeline, deep learning models scale poorly. Their massive compute requirements generate severe latency and prohibitive infrastructure costs. This introduces inference cost, the exact amount of memory, energy, and CPU time required to execute a single prediction in production. To reduce this cost, engineers use quantization. This technique strips away excess data by converting highly precise floating point values down into a much shorter integer format. This reduces the memory footprint and accelerates mathematical operations, but it introduces a strict trade-off, risking a drop in accuracy during complex reasoning tasks. Another approach is pruning. By identifying and removing redundant parameters or low-importance connections, the network is snipped down to a leaner, faster structure. For massive models, knowledge distillation transfers the learned outputs of a heavy teacher network directly into a smaller, highly efficient student model. Hardware-aware inference optimization is a mandatory final step. It transforms a computationally intensive theoretical model into an economically viable system, optimized for low-latency inference. This blueprint maps the complete AI architecture, moving from raw data to an operations pipeline into a specific learning paradigm and network topology, and finally through inference optimization, creates a unified technology stack. This holistic, end-to-end system design represents the transition to Software 2.0. In this framework, system behavior is no longer explicitly written by human programmers. It emerges entirely from data curation and strict architectural constraints. We have moved from the era of manual, rule-based computational programming into an environment driven by autonomous statistical pattern recognition. Modern artificial intelligence engineering depends on the mastery of this entire stack to translate abstract mathematics into realized intelligence at scale.